Okay, let's go back to pipe flow. So let's discuss now something called the friction factor. So this comes from a consensus in engineering, which is that we usually non-dimensionalize many quantities. It makes things easier, and in particular, things that have to do with pressure are often non-dimensionalized with the dynamic pressure. So in this case, it is common to non-dimensionalize the pressure drop by the dynamic pressure. Anybody remember the dynamic pressure? We have a 1/2 and we have a v squared, and then if you wanted to sort it out, really what you would do is check on the units, right? Because it has to have units of pressure. It's rho v squared. So let's go back to our expression that we had for the pressure drop in the pipe with a parabolic Poiseuille flow, and that is delta P is equal to 32. We just had this times mu L, the distance along the pipe, times the average velocity divided by d squared. And so if we want to non-dimensionalize this by the dynamic pressure, we have delta P over 1/2 rho v squared. The average, of course, is what we want to use here. It's 32 mu LV bar over d squared times 1/2 rho v squared, and that gives us delta P over 1/2 rho v squared is equal to 64, 32 times 2, and we're going to reorganize these things a little bit. We have mu, we have a rho over here, and I have a v squared, so I'm going to write those here, mu, rho, just one v I'm going to use here. I'm going to have one d, right? I actually, one of the v's cancels out, and I have one d left down here, and I have the L at the top. Do you recognize this guy here in the middle? One over the Reynolds number. Excellent. Very good. So this is equal to 64 over the Reynolds number times L over D. So this here for laminar flow we're going to call the friction factor F equals 64 over Reynolds. This is for laminar flow. Remember, all of the results so far are for laminar flow. So we have, in that case, as a function of this F, we have delta P is equal to F times L over D, and I'm going to just put the rho v squared over 1/2 here. This is our dynamic pressure.
Hold true when the Reynolds number is small compared to
2000, yeah. So it has to be smaller than.
If it goes over that relationship isn't true.
Exactly. It is not true anymore. Only for laminar flow. In terms of the shear stress, we had delta P is equal to 4 L over D times wall shear stress. That's one of the expressions we had a couple of slides back. And so we can write F by combining these two as 8 times wall shear stress divided by rho v squared, the average. And so this shows the friction factor as a non-dimensional wall shear stress. You see the relationship there between them. That's why we call it the friction factor. It's like a non-dimensional wall shear stress. And I didn't leave any space, so I'm going to clear up here now that we can write the head laws. In terms of the friction factor. And the head loss is going to be, remember, is P over gamma. So delta P over gamma is F L over D rho v squared over 2G. That's the head loss in terms of the friction factor. Yes?
Is that still the average velocity?
Yes, it's the average velocity everywhere. So what happens for turbulence flow? As you were pointing out, for turbulence flow, we don't have this neat, clean expression, so we can't do that. So what can we do for turbulent flow? So recall that we found for laminar flow that in a pipe that delta P over 1/2 rho v squared is equal to 64, and we had mu over rho v average d L over d. So you see this is a function of Reynolds number and L over d. Two non-dimensional numbers, the Reynolds number and this non-dimensional, this combination of the length and diameter. Now, in the case of turbulence flow, in fact, we can use what's called dimensional analysis We'll do a little bit of that towards the end of the course, depending on our available time. So we can use dimensional analysis to determine that in addition to Reynolds number, and L over D, the pressure drop in a section of pipe also depends on the roughness of the pipe. Or perhaps in physical terms, if you can imagine that as you go to higher Reynolds numbers, we have the situation that we discussed in terms of a boundary layer. We have a very thin region near the wall where all of the viscous effects are confined. If the Reynolds number is very big, the boundary layer is very, very thin. And so if the surface of the pipe has kinks, those kinks are going to interact with the boundary layer and are going to change the features of the flow there. For laminar flow, it goes into parabolic. You see that there isn't really a thin boundary layer. The viscous effects are equally felt all across the diameter of the pipe. And so the little kinks in the surface don't really matter. If I want to give sort of a hand-waving explanation of this. It can be worked out more rigorously, but we are saying that in terms of the turbulent case, we have to introduce, in addition, the effect of the roughness of the pipe. So let's consider this epsilon to be some measure of the surface roughness. Of the pipe wall. And so for general turbulent flow, the pressure drop, delta P over 1/2 rho v squared, is going to be a function of not only Reynolds number and L over D, but also a non-dimensional measure of roughness, epsilon over D. So we have an additional influence to consider, making a parallel with the laminar result. This epsilon over D is what's called a relative roughness. And it turns out that for commercially available pipes, you can get the value of epsilon for different, concrete, steel, and so on. You get these from either the technical sheets, or there's tables in the books. You'll find tables in the handbooks, your engineering handbooks. You find tables of this epsilon. So with your diameter of the pipe that you're designing, you can get the relative roughness. So the question is, of course, what is that functional relationship? And as you know, we are not able to find a closed form solution from the Navier-Stokes for the case of turbulent flow. And the only result, the only resource that we have used over the years is to do extensive experimentation to obtain something that we can use for this functional relationship here. We can probably agree, you will probably agree that the pressure drop should be proportional to the length along the pipe, like in the case of laminar flow. That functional relationship should continue to be linear. So if we take that out, as a linear functional, this is also verified by experimental results. Then we would have delta P over 1/2 rho v squared has to be equal to L over D. So here we have a proportionality and some function, unknown function, psi, some unknown function here of Reynolds, and epsilon over D, the relative roughness. We could also express this in terms of a friction factor, or an unknown friction factor. In terms of an unknown friction factor, delta P is equal to F times L over D times rho v squared over 2, just like before, but the friction factor now, F, has to be equal to a function of Reynolds number and epsilon over D. So this functional relationship is not available to us from Navier-Stokes equations for the case of laminar flow, for the case of turbulent flow. For laminar flow, we did find it. It was 64 over Reynolds number. And it didn't depend on the surface roughness. But for turbulent flow, there has been extensive experimentation made to obtain this friction factor, and these results have been consolidated in a plot which is called the Moody chart. So remember, we said friction factor is a function of Reynolds number. Here's the Reynolds number. And surface roughness. Here is the surface roughness. And here on the left, you don't have anything, but that's actually F. What you read here from the left is the friction factor as a function of Reynolds number and surface roughness. So for a given pipe, a given diameter, you get your relative roughness and say it's this one. You follow this line to the value of Reynolds number. Suppose Reynolds number is 10,000. 10,000 with this line, here it is, and then you read the friction factor from the other side. We'll do a example problem in a moment, and you can see how the results come out. Okay, an actual realistic example we'll do in a moment. But I want to point out several other things from this chart. In laminar flow, we have, of course, a linear relationship, which is 64 over Reynolds. That's for laminar flow, as we expect. For turbulence flow, with the very, very low, very large Reynolds number, so it's over here, very large Reynolds number, the friction factor practically becomes a function of epsilon over d only, and the function, it practically doesn't change any longer with Reynolds number for very large Reynolds number. And that makes sense because very large Reynolds number means the boundary layer is very, very thin, and the friction is completely dominated by the roughness because the kinks of the surface completely penetrate the boundary layer. Question?
So, the friction force is almost constant if you have a large Reynolds number and surface roughness. So, for all Reynolds numbers, if you have a large enough surface roughness, your friction force doesn't seem to change. Like your top line.
This line doesn't seem to change very much. If it's because if it's very rough,
Right.
Basically the effects of surface roughness penetrate quite a bit into the whole flow will be affected by it. All the eddies. Remember, turbulent flow is going to be a mixture of different eddies of different sizes, and they will, near the surface, they will interact with the surface roughness. And so if those kinks are very high, very large, then that's going to be transported, that effect is going to be transported all the way through the diameter of the pipe. And what we read here, we call is a friction factor, not a friction force. It's a non-dimensional factor. It's a shear stress that has been non-dimensionalized. We could check the units of that. F is non-dimensional, L over D is non-dimensional, and delta P over gamma has units of length, right? And rho. So can you work that out? We're multiplying by velocity, length divided by time squared, and in the bottom we have acceleration.
Rho shouldn't be there.
So rho shouldn't be there. It cancels out. Okay. Typo. Find a typo. Congratulations. So everybody fix your notes. So you know where it is. It says head loss in terms of it's just a little bit behind, a little bit behind. Let's see. Let me clear this up. And we had, let me write it down. We had delta P over gamma equals F. This was in terms of the head loss, L over D for the laminar case, and this is what I had, rho V squared over 2G. But this row shouldn't be there. Okay, I forgot to cancel it out. We just confirmed. Everybody got that? All right, back to the Moody chart. So we're looking at the Moody chart here. You see that we've got laminar flow down here, 64 over Reynolds. We have that for large Reynolds number, practically the effect of Reynolds number drops out, and it is only a function of the roughness. What else do we have? So in here is completely turbulent flow, and the laminar layer, the boundary layer is so thin that the surface roughness completely dominates, we were saying. Now for flows with moderate values of Reynolds number, around here we have dependence on both the Reynolds numbers and the roughness around here, all of this area. I can clear a spot here and say this is both a function of Reynolds number and roughness. And also we note that there's a transition range where we don't know F really, because in the transition range the fluid can behave as laminar or turbulent intermittently, and so we really can't tell. In that area the values are not, these are not known. They're indeterminate. So no values given between what should be the transition range, so between 2000 and 4000, that's the transition range in pipe flow. The values are indeterminate. Now the other thing that we can note is that the value of the friction factor is not zero even for infinitely smooth pipes, because of course there's a no-slip boundary condition. So there's always friction. There's always, even if the pipe is infinitely smooth, we believe in the no-slip boundary condition there. So that's what happens here. Even if this infinitely smooth case, F is not zero, doesn't mean that there's no friction. There still is friction. And the roughness for the commonly known pipes are of course obtained from handbooks and so on. You look confused. You have a question? Okay, so a headache. Yeah. It's not a force. Yeah, we'll do an example in a moment. Yeah, so that's right. Before I do an example, here's the example, but before we do that, let me just give you that. Well, of course, this is quite old. Actually, the Moody chart comes from a publication by Mr. Moody in 1944, and at the time we didn't have computers, or the computers were only big, huge machines in some army lab. Today we have all of these tabulated, and it's more useful to use expressions, analytical expressions. Actually, there's been a huge amount of work to develop analytical expressions since the publication of Mr. Moody in 1944. So let's see a couple of these. Do I have time for the example afterwards? Yes. So, like I was saying, there's been many attempts to get analytical expressions. The most famous, first let's note that Moody already said in his paper that the results on the Moody chart are experimental. So there's some error there. There's an error bar associated with each result. And so here Moody already stated that the accuracy in the Moody chart was about 5% for smooth pipes, and plus or minus 10% for rough pipes, for the rougher end of the chart. So considering that, if we're going to do a fitting of those results, we don't have to find like the most exact fit, because if already the experimental results have 10% error, then any formula that fits within that accuracy range is going to be fine, right? So the most famous one for a long time was Colebrook. The Colebrook formula. Don't let it confuse you that this is from 1939 and the other result is from 1944. The results were known amongst the researchers, and just the most famous paper of Moody's 1944 paper. But this guy had an empirical fit of the pipe flow pressure data. And it looks like this. 1 over square root of f is equal to minus 2.0 log of epsilon over d divided by 3.7 plus 2.51 divided by Reynolds square root of f. It's an implicit formula for the friction factor f, which means to use this, you need to use an iterative method. So it's not very convenient, but he was able to obtain this within the accuracy of the experiments. And this, of course, applies for Reynolds above the transition value, right? So only recently there's been some more nice formulas. There's this one called Haaland. That's the way you write it. I'm not sure how you pronounce it. From 1983. And he found a nicer looking one, approximation of the implicit. So this is again an approximation of the previous formula, an approximation of the experiments. But it is also to within the accuracy of the experiments at plus or minus 10%. Note that if the accuracy of the results is plus or minus 10%, it doesn't really make sense for you to calculate things with 5 decimal places, okay? So just be aware that you're working with fitting of experimental results. So this one looks like this: 1 over square root of f, still we have that one, but at least f doesn't appear on the other side, minus 3.6 log of epsilon over d over 3.7 to the power 1.11 plus 6.9 over Reynolds. There's been several other formulas proposed over time. This is the one that appears on the textbook, but not much explanation is given where it comes from. So here I'm giving you a little bit of context. It's an approximation of this other formula, where this formula is an empirical fit of the results. Now let's do an example, and just enough time before the end of class to do an example so that it becomes more clear. I hope. Okay. This is actually the example given by Mr. Moody in his 1944, this famous 1944 paper. Because it's such an old example, is of course on British units. It's just the metric system hadn't yet been disseminated at that point. So compute the head loss and the pressure drop for a 200 feet horizontal 6-inch diameter asphalted cast iron pipe. It's a typical pipe used for moving water around. And the water is moving at a mean velocity of 6 feet per second. So that would be like a typical application of water distribution. Cast iron covered with a layer of asphalt inside. And this you can go and look it up from handbook or something to obtain the roughness. But let's write what we have so far. We have diameter. Let's put it immediately in feet. 6 inches is 1/2 or 0.5 feet. The length is 200 feet. The velocity is 6 feet per second. Then we have water, so the properties are density equals to, and this is going to be, this is the units I hate, slug per cubic feet. So these are the nasty units that we don't discuss anymore. But let's just carry on. In the book there's conversion factors for these things and the values of the water properties, density and viscosity. The viscosity depends on temperature, so you have to kind of come up with a temperature that you want to choose for the problem. So I just went in and chose 68 degrees Fahrenheit, or this is the one used in the paper, I'm not sure, and times 10 to the minus 5, and the units are slug divided by feet second. Okay, let's truck on with these numbers. The first thing we want to do is calculate the Reynolds numbers and the relative roughness. So the Reynolds number is rho v d over mu, and for this we have 1.94 slug. I'm going to put all my units there so to see that it makes sense. Feet cubed. V is 6 feet per second. D is 0.5 feet, and mu is 2.09 times 10 to the minus 5 slug divided by feet second. And so we're very lucky that the slugs cancel out, so we don't have to worry about them anymore. And indeed all units cancel out because this is Reynolds numbers and non-dimensional. So they should all cancel out. We have feet cubed, and then we have 1, 2, and this one at the bottom because at the top it also cancels out, seconds cancel out, so on. Right? So the numbers, we put them in the calculator and we get 279,000. Definitely turbulent, right? Without a doubt, this is going to be turbulent. So we need to obtain the roughness for asphalted cast iron from some tables. And in fact, I've put a link on Blackboard well, I have to activate those links actually, now that I think of it. There's a table there for roughness data for different type of commercial pipes. But there's also information in the books, and you can find them all over the place. So we look this up. We look up the roughness for the asphalted cast iron pipe. And get epsilon equals 0.0004 feet. And so we get the relative roughness, epsilon over d is 0.1230 divided by 0.5, and I get 0.3 zeros and an 8. This is, of course, without units, it's non-dimensional. So next we need to find the friction factor from the Moody chart. And I've actually printed out several copies of the Moody chart. I'm going to pass them around now, so everybody's got one. Okay, who's got the friction factor found and ready to spit out? 0.02. Already, we got some experts on. So, not on the Moody chart. So, second step is look up F on Moody chart, and we get F equals 0.02. Very good. That's the same thing, approximately 0.02, and it's the same thing I got. Just reading from the plots. Everybody can see that? Yes, you're happy? Okay, so we've got F now. What we need to do next is to calculate the pressure drop and the head loss from the equations that we have. So I'm going to clear the annotations here. Everybody's written that down? Okay, good. So I'm going to clear these, and now the next step is, now step number 3 is to calculate HL, head loss, and pressure drop from the equations that we have, and they were head loss is equal to F times L over D, V squared over 2G. That's correct? Did I get that right? I think so. Yeah. So here I don't have the extra row, do I?
No, but isn't that what I would have done?
No, remember that we said for turbulent flow we can write it the same way. The only difference is that the friction factor now is not 64 over Reynolds, it's some unknown function which we obtained from the Moody chart. Yeah. And so, but we have it now, 0.02, and we have L over D, 200 divided by 0.5. We have V squared, 6 feet per second, squared divided by 2, and G in the units here, which are 32, which is 32.2 feet second squared. And that gives me approximately 4.5 feet. That's the head loss. It must have units of length. Delta P is gamma times the head loss. We can actually do it more. We can do a shortcut. We already have the head loss, so we can get delta P easily here from rho G head loss, and that gives, it's 1.94 slug divided by feet cubed. Let me give you the conversion for this strange unit here. So 1 pound of force is equal to 1 slug, that's where it comes from, 1 slug at moving at 1 feet per second squared. So that you can plug it in here. It's the equivalent here of a. It's a strange thing, isn't it? It's a measure. Slug is a unit of mass. Yeah, but it's exactly. But it's a unit of mass. It's a strange unit of mass. I've never gotten used to these units myself, and so I find it a bit hard. But and we get, with the conversion here, correct conversion, 280 pounds of force divided by feet squared. And then this is going to allow this pressure drop, this information is going to allow you probably to dimension a pump, to dimension the, remember when we used the pressures to calculate bends, the fittings of the pipe. You can calculate now the forces with all of these things and so on. This will be helpful in that setting. Okay?